Professor Muhammad, and this is Dynamic Analysis Fundamentals class, and I'm going to explain today about this is Response Spectrum, Part 3, and I'm going to talk about some issues related to dynamic analysis, but I'm not going into the details for the dynamic analysis, just an exposure to dynamic analysis and the links with the seismic design. So now let's go to our main title. So again, we are under the main title as we started our sorry for this, we started our course series. This is the part related to the fundamentals of dynamic analysis, which is going to be linked to seismic design in general. And we are under the subtitle of Response Spectrum Concept, and we are going to talk today about three different points, actually important points. The first one is going to be the displacement, velocity, and acceleration response spectra. And the second, I'm going to talk about the combined displacement, velocity, acceleration spectrum, which is, we call it tripartite response spectrum. And then I'm going to talk about pseudo versus true values for velocity and acceleration. So these are the main topics that I'm going to handle today, and I hope that it would be easy for us to understand it. Okay, now let's go to the first thing, which is, or the first item that I'm going to explain today, which is the deformation response spectrum. Okay, already I have introduced or explained response spectrum before, the main concept and so on, but today we are going to talk about the deformation response spectrum in particular. Okay, so if we're going to look to any time history of an earthquake, so for example, if we are going to choose El Centro, ground motion, we can plot the time history. We call this the time history, as I have explained it in the previous videos. We can plot this time history, which is going to be between the time elapsed and the vertical axis is going to be a ratio between u double dot g. This u double dot g means that it is the ground acceleration, and this g means that it is the gravitational acceleration. Commonly we use this term in order to express the history or the acceleration history of any earthquake. El Centro is considered to be one of the most famous time history records used in academia and for engineers also, and for design companies and so on. So this kind of history is commonly, you're going to see it frequently, and if you are interested in earthquake engineering in general. And this is considered to be the acceleration recorded for the first 30 seconds. So we only took like 30 seconds and we plotted them here. Okay. Now we are going to the part of how we can develop the response spectrum, First of all, we said that response spectrum is as if it gives information about different structures, and these different structures, they are going to be single degree of freedom system. So we are going to make linear time history analysis for a single degree of freedom system that has specific characteristics. It has mass, okay, and it has stiffness, m and k. These two values, we can represent them using the natural period of this system. The natural period of this system. So whenever that we are dealing with response or with a single degree freedom system, we can represent this system simply by Tn, because it is representing the mass and the stiffness. Okay, already I mentioned about this issue also in the previous video. You can take a look on it. Okay, so we are going to take one single degree freedom system with, let's say, 0.5 second natural period, and then we're going to have another single degree of freedom system with another t which is 1 second, and a third one with another Tn or natural period with 2 seconds, and so on and so forth. These are only examples, but actually we are able to use more and more. For the construction of this response spectrum, we need like hundreds of single degree freedom systems. Only 3 of them here we are going to study for illustration purposes only. So we are going to say that this system is having this natural period, and we're going to assume that it is going to have damping ratio of 2%. This is common for all of them. They are going to be 2%. This means that when we are going to draw our response spectrum, as we are going to see shortly, this response spectrum is going to be for a damping ratio equal to 2%. Okay, so this is what we are doing, or this response spectrum is only for damping ratio of 2% as it is mentioned here. Okay, what we are doing here, first, for the first single degree of freedom system, we are going to make linear time history analysis, and we are going to check what is the response here. This vertical axis is the deformation u in inches. Okay, so this is the deformation u in inches, and this is the t, which is the time elapsed. This is the time which is going to be measured in seconds. So we are dealing with 30 seconds only, as we mentioned before. When we make the linear time history analysis for this linear elastic single degree of freedom system, we need to plot the response based on the Hamel's integral and based on the differential equations that I have explained in the previous 2 videos for each point of time, right? For each point of time. This would be done for us for each point of time. Okay, along this t, we are going to obtain u, which is the deformation. Then we're going to plot it here. Then when we are going to look to this plot, we will be going to be interested in one value, which is the maximum, the peak value. This is commonly, as a designer, as an engineer, you are interested only in the maximum deformation of the system, of this equivalent or this single degree freedom system. So we found that when we done this for this system, we found that the maximum deformation or the peak deformation is 2.67 inches. Okay, so that's good. Now let's go to the second part, which is the second system. We are going to use this system with Tn equal to 1, and we are going to make linear time history analysis, and we are going to plot the deformation per each point of time along the 30 seconds, and we are going to look to the peak value. We found it to be 5.97. Similarly, we are going to do it for the third system with 2 seconds, and we found that when we plot the displacement or deformation at each point, we found that there is one peak value, which is 7.47. From here, we are going to say that the peak values for each single degree of freedom system is the most important thing for us in case of design. Then we are going to plot it. We are going to plot these deformations, these maximum deformations. So we're going to plot the maxima only. So we're going to plot it on the vertical axis for this plot, and we are going to call it D or U node. This means that the peak, okay, the peak deformation. And we are going to plot on the horizontal axis the natural period. Take care, it is natural period, not T. Okay, T, it is the elapsed time for the record itself or the time history itself. But T, it means that the natural period of the single degree of freedom systems that we are going to utilize. We have the first one, it has 0.5, so we are going to have here it's supposed to be 0.5 seconds. The response was 2.67, as you can see it here, 2.67, and at 1 was 5.97, which is here, and at 2 it was 7.47, which is this one. Then we are going to conduct this for hundreds of degree of freedom systems. Hundreds of degrees of freedom system, and we are going to find the plot. This plot is going to be called the deformation response of the system of 3 single degree of freedom system. Actually, this is the deformation response spectrum, okay, with beta with the damping ratio equal to 2%, because as I said, this is only for 2%. Why? Because we used in our analysis the damping ratio to be 2%. If you remember, this is in the differential equation. It was always given as input parameter, okay, for the differential equation. In this case, we have drawn the response spectrum, deformation response spectrum, okay, for damping ratio 2%, as we said. Okay. Now let's go to the something called velocity response spectrum. Velocity response spectrum. Actually, for velocity here, we are going to use the word pseudo before velocity. I'm going to explain about this word at the end of the video. Okay, so I'm going to explain about why we use this word. But anyway, remember that we are going to talk about the velocity response spectrum, not deformation now. Okay. Now, the pseudo velocity response spectrum is a plot of velocity. Again, it's a plot of velocity, not deformation here. Okay, as a function of the natural vibration period, which is Tn, or the vibration frequency, which is Fn. Okay, so this is similar to what we have done for the deformation response spectrum. We used in the deformation Tn. Okay, the prefix pseudo is used for V because V, it is not equal to the peak velocity. We call it peak velocity, or the true, we can use this word better, which is true peak velocity, although it has the same units for velocity. I'm going to explain about it. Do not bother yourself with this term now. Just remember that the term pseudo means that it's not true. It's not the true peak velocity. It is like false one, okay, or approximate one. It's better to say it's approximate, not to be false. The word pseudo actually, I think that it's a little bit misleading. We should use the approximate word here, not pseudo. But as I said, I'm going to explain about this issue later. For a given ground motion, the peak pseudo velocity, V, for a system with natural period Tn can be determined from the following equation. I'm going to explain the following equation using the deformation of the same system from displacement response spectrum. This means that we are going to use displacement response spectrum that we have plotted a few slides before in order to obtain the peak pseudo velocity response spectrum. So what is the equation that we're going to explain? So this is the equation here. The equation is simple, that V is going to equal, this is the pseudo, as I said, pseudo velocity, okay? It equals to omega n. Omega n, it is the natural circular frequency of the system, which is 2 pi over Tn. Tn, it is the natural period, and omega n is the natural circular frequency, and they are related through 2 pi over n, as we can see. So the velocity here is going to be easy to be calculated. It's going to calculate it easily. It is going to be equal to omega n times d. D already we have obtained it from the previous slide, the deformation response spectrum. So it is going to, the pseudo velocity is going to equal 2 pi over Tn times d. Okay, so let's have an example based on what we have explained for the deformation response spectrum. As an example, for a system with Tn equal to 0.5 second, as we have done before, and with damping ratio equal to 2%, d, we have obtained it in the few previous slides, right? It was 2.67 inch. This means that our pseudo velocity would equal to omega n, which equals to 2 pi over Tn, is Tn, times d, times this value. So we are going to have 2 pi over 0.5 times 2.67. It equals 33.7. 33.7. Okay. Similarly, we can do it for Tn equal to 1 seconds. We're going to find that d was 5.97. Then pseudo velocity equals to 2 pi over Tn times d. So it is going to be 37.5 is the second value. And the third value is going to be repeated for Tn equal to 2 seconds. And the same force damping 2% and d equal to 7.47 inch. Already we have obtained it before. Then we substitute in this equation 2 pi over Tn times d equals to 23. So we are going to plot this as we have done before. We are going to plot this. These values going to be plotted here. It is like 33, and after that we have like 37, and then it is 23, something like this. Okay, this is what we are going to see in the next slide here. So we have the first value 33.7. It is corresponding to this is the deformation response spectrum. So this one, it is deformation, okay, response spectrum that already we have drawn last time or previous slides ago. So we have this 2.67, the corresponding is 33.7 after multiplication by 2 pi over n, and here 5.7. The value for the response or the pseudo velocity response spectrum is going to be 37.5, and here 7.47, it is going to be 23. This is for 0.5, this is for 1, this is for 2. Here, as I said, horizontal one, it is Tn, vertical one is going to be pseudo velocity. The units are inch per second. This is velocity, okay? And this is what we call it, pseudo velocity response spectrum. Pseudo velocity response spectrum. Okay, so now we could map between the deformation response spectrum and the pseudo velocity response spectrum. Now let's go to the third important item, which is pseudo acceleration response spectrum. Pseudo acceleration response spectrum. So here acceleration instead of velocity, and again pseudo, which means false or approximate. For a given ground motion, peak pseudo acceleration A for a system with natural period Tn, if the natural period is Tn, and damping ratio can be determined from the following equation using the peak deformation. Again, the peak deformation of the system, which is coming from the deformation response spectrum, is going to be used again in order to obtain the peak pseudo acceleration. In this case, it equals to omega n squared raised to the power 2 times d is equal to 2 pi over Tn, the same as we said, but it's raised to the power 2 times d. Okay? And then it is going to be very easy for us to obtain the acceleration, the pseudo acceleration response spectrum. We're going to follow the same routine that we have done before. For Tn, d was 2.67. Remember that we are talking about damping ratio, fixed damping ratio, which is 2%. Tn 0.5, d 2.67. Then we're going to substitute in our equation A equal to omega n squared d, 2 pi over Tn times d raised to the power 2, 2 pi over 0.5 for our case, times d equals to 1.09 g. Okay? And the second, we're going to follow and repeat it again, Tn equal to 1 second, and the peak deformation value was 5.97. Substitute in this equation, put the Tn here, raised to the power 2, d here, then you can obtain this is the value of the pseudo peak acceleration at t equal to 1 second. Similarly, we are going to do it again for Tn equal to 2 seconds. D was 7.47 as we have explained before. Then we found that A going to have 0.191 G. Let's plot them here. This is actually what we have obtained. This is the pseudo acceleration response of single degree of freedom system to al centro ground motion for different natural periods. So here this is Tn, okay, 0.5 second and beta equal to 2. This is the total response spectrum. We're going to find that the maximum A is 1.09 G. Take care that we are talking here, the vertical axis is the acceleration or the pseudo acceleration. When Tn equal to 1 second with damping ratio 2, found 0.61 is the maximum value, 0.61 G. And here it is going to be 0.191 G, where Tn equal to 2 seconds. So we have the values here. This is the maximum here, this is the maximum here, and this is the maximum here. Okay? Then we can plot them. Yes, we can plot it here. So the first value, which is 0.5 here, it is 1.09 as we explained. It is corresponding to this value in the deformation response spectrum, and it is corresponding to this value for velocity response spectrum, pseudo velocity response spectrum, and it is going to be mapped into the acceleration or pseudo acceleration response spectrum as 1.09. Similarly, for this value for 1 second, for the velocity it was 37 something, for the acceleration it is 0.61, and here for 2 seconds it's 0.191. Okay. Okay, so there is something that needs to be looked here, and we need to notice here. Whenever we increase the natural period of the system, it seems that as if the deformation is increasing, right? To some way it is increasing. But whenever it comes to the velocity, pseudo velocity and pseudo acceleration, okay, we're going to find that it's not like this. It goes up and then like making some jagging here and then going down after that. Similar here in the velocity response spectrum, increasing the natural period is going to, there is no specific pattern that we can say, but at least in this part here it is almost the average is the same, but after that the pattern cannot be predicted well, right? So this is, keep it in your mind because we are going to talk about this issue later. Okay, so now we have the three different response spectra, deformation, velocity, and acceleration response spectrum. Okay, now the second or the next level is to put all the three response spectra on the same graph. And this is what we call it tripartite response spectrum, meaning combined displacement, velocity, acceleration spectrum. Okay, it is going to be combined. So the tripartite means that it is combined with three different graphs. They are going to be on the same graph. Okay, and we call it tripartite response spectrum. Okay. Some hints that we need to keep in our minds before going into this, that each of the deformation, pseudo velocity, and pseudo acceleration response spectra for a given ground motion contains the same information. That's very important. No more and no less. No more, no less means that the response spectra or the velocity or acceleration response spectra, they are similar. They are similar. They are having the same information, keeping the same information, and saving the same information. Because commonly, if you look, we said that V was equal to omega times d. So it is a constant multiplied by d. And A, which is the acceleration, equals to omega squared d. So actually they are the same. They are the same. Only there is a constant that is being used, which is the natural circular frequency of the system that is used, okay, to give three different components. The three spectra are simply different ways of presenting the same information in structure response. Okay. Knowing one of the spectra, the other two can be obtained by algebraic operations using the following. As we said, because they are using algebra or algebraic operations, we can find that V is related to d through omega n. Okay, so V equal to, or the pseudo velocity equals to omega n times d, and in the same time v equals to acceleration over omega n, right? So also this is some common, that is v is going to equal omega, which I said many times, this is omega, 2 pi over Tn times d, and v equals to a over omega, which is the reciprocal of omega. Tn, I mean that multiplied by the reciprocal of omega, which is Tn over 2 pi. Okay, so they are, as you can see, algebraically, or using algebraic operations, we can manipulate through them and we can obtain A, V, or D easily. Okay, so now let's see the tripartite response spectrum, okay, the combined, how we can draw it. Actually, we are not going to draw it by ourselves. It is going to be given to us here, and just we want to understand it. That's it. No need to construct this tripartite, because this is detailed in the in my dynamic analysis course. This is how to I teach how to draw the tripartite response spectrum, but here for this course only you need to understand what is the meaning of it, okay, and how we can extract information from it. That's the main and the major point or advantage of this combined response spectrum. Okay, now let's go to the axes, because it is full of axes here. The first one, the horizontal one, is going to be Tn, which is the natural period of the systems. And the vertical axis, as you can see here, it is V, which is the pseudo velocity, okay, the pseudo velocity. Then we have a couple of axes here, and they are having or making a 45-degree with the horizontal. So here, the first one, which is this axis, we call it the deformation axis, okay, and the perpendicular one, they are perpendicular to this one, okay. This one, it is the acceleration, pseudo acceleration axis. Okay, so we have 4 scales here, okay. All of them, they are logarithmic, using logarithmic scales, logarithmic scale. The horizontal and vertical, they are exactly the same, okay. But when it comes to the 2 inclined axes of the D and A, they are logarithmic scale, but a little bit different than the scale of the vertical one. That's what we want to see, okay. This curve now is only one curve, it's not 3, but it gives 3 different values for the deformation, velocity, and acceleration. So this curve for damping ratio of 2%. If we take this point, for example, on this curve, okay, we're going to see at natural period of a system 2 seconds, we're going to look to it here on this. This point is going to give us 3 different pieces of information. The first one is the deformation. The deformation is 7.47 on the D scale. And on the A scale, which is the acceleration scale, we found that here this value is 0.191. And on the velocity scale, we found that this value is 23.5. So it gave us 3 different values, which are the maximum deformation and the pseudo acceleration and the pseudo velocity. These are the 3 here. Already we have explained, or we have calculated them before, right? If you go back here, yes. So at 2 seconds natural period, this is D, 7.47. This is V, 23.5. This is A, 0.19, right? Similarly, if we go to the next one here, this is 2 seconds natural period, 7.47, 23.5, 0.191. This means that this graph is much easier to understand and wealth of information. It is considered to be given like 3 pieces of information in the same graph, which is very nice and easy. And you are going to find that there is additional advantage for this graph. I'm going to talk about it later. Okay, so first of all, we have this, we call it combined DVA response spectrum for El Centro. We are talking about El Centro now. We can do this for any earthquake, okay? This is only for El Centro now, but you can do it for any earthquake. It's easy to be constructed for any earthquake. And remember that we used only damping ratio 2%, okay? In our equation, it was 2%. The first time that this graph has been introduced, it was introduced in 1960 by Velocitus or Velocitus, I think, and Newmark. Okay, Velocitus and Newmark. Newmark is very famous in earthquake engineering, and also Velocitus. I'm not sure about his name. I hope that the way that I'm pronouncing the name is right, but it seems like Velocitus. Okay. Okay, he seems to be like Italian or something like this. But anyway, okay, this is the names, and this is the first time this graph has been introduced. It was in 1960. Okay. Now let's go to the, yes, actually in this graph I was explaining, okay, the vertical and horizontal scales for V and Tn are standard logarithmic scales. We call it the standard. So this one here, if you look here, it is logarithmic scale for V and also logarithmic scale for T. Okay, the two scales for D and A, which is D and A, okay, sloping plus 45 degrees and minus 45 degrees as I showed it here, okay, respectively to the Tn axis, are also logarithmic scale but not identical to the vertical scale. That's the point here. They are logarithmic, but they are not identical to the vertical scale. Okay, we need to keep in our mind this piece of information, but they are very easy to be constructed, as I said, and you can get the information very easy from this graph. Okay, let's jump to the next slide. Let us ask this question, that is, why do we need 3 spectra when each of them contains the same information? So as we said that before, that all of them, they are like the same, they can be used interchangeably, right? But they are giving different information, and each information, it represents a physically meaningful quantity. That's the point here. One of the reasons is that such a spectrum directly provides a physically meaningful quantity. A physically meaningful quantity. What does it mean? The deformation spectrum, which is giving to us D, the maximum deformation or the peak deformation, okay? The deformation spectrum provides the peak deformation, which is very important for us whenever that we are designing and in general, okay? So it is related to the deformation for our design for the system. And the pseudo velocity, whenever we talk about velocity spectrum, it is related directly to the peak strain energy stored in the system during the earthquake. So whenever I say that the velocity is like 7 point something, this means that the strain energy, ESO, means that strain energy stored in the system equals to, do you remember this curve? It is mv squared over 2. This is the strain energy calculation, right? And from here, if we know v, and of course m is known, it is constant, then we can obtain the strain energy easily. As we are talking about peak values for velocity, this means that we are talking about peak strain energy. Peak strain energy. Okay, so this is for velocity. What about the pseudo acceleration? What is the quantity or the physical quantity that is giving to us, the physical meaningful quantity for us? It is related directly to the peak value of equivalent static force or base shear. Do you remember that whenever we are talking about M from Newton's law, A times M gives us what? Yes, the force. What force here? The force that if we have a single story, for example, or even a single degree of freedom system, okay, the force that is going to be developed here due to the inertia force, this is what we call it FSO. And this is going to be equal to the shear of the system, which is VBO. Okay, so the force that is going to be developed due to inertia force, or the base shear that is going to be developed to counterbalance this inertia forces, which is VBO, they are going to be given through the pseudo acceleration if it is multiplied by m. If it is multiplied by m. Okay. Now let's go to the next part. We're going to talk about the maximum elastic displacement for single degree of freedom and multi-degree of freedom system. This is actually important for us. Why I'm choosing only the displacement here and why it is multi-degree of freedom system and single degree, because it is commonly used in seismic analysis and design and in ASCE. We are going to talk about these displacements. Displacement are commonly used because it's the main engineering demand parameter that is commonly used in earthquake engineering, okay? Even compared to the velocity or acceleration, but displacement is dominant, okay? Other two quantities are very important as well, but if we're going to rank them, displacement is going to be number one. And whenever we are talking about response spectrum in general, whenever that we're talking about response spectrum for acceleration or kind of velocity or deformation or whatever, that we are talking about single degree freedom system. But actually our life is, you know, we have like multi-story buildings. So we are dealing with something that is, we call it multiple degrees of freedom system, not single degree. So we need to know how to obtain this multi-degree freedom system deformation or displacement from our single degree freedom system. Okay? Okay, let's have a look on this and see how it works for us. Okay, so the calculation of the maximum displacement for single degree freedom system, we're going to talk about it, and in the next slide we're going to talk about the multi-degree freedom system. Okay, so we're going to talk about the two. For SDF, response spectrum analysis is a means of using acceleration response spectra to determine the maximum forces and displacement in a structure. This is something important that it's a little bit flipped for us. Commonly, what is given for us is the response spectrum, acceleration response spectrum. This is commonly given for us. I mean that it's available for us always. What is not available, what we are seeking and searching for, is what is the delta of the building? What is the displacement of the building? Okay? So in the derivation of the response spectra that we have explained shortly, we were starting from the deformation, then multiplied by omega to get the pseudo velocity, and then multiplied by omega again to obtain the pseudo acceleration. But in reality, we are seeking or searching for the deformation. We want to know if we have a single degree freedom system, okay, and there is a kind of like earthquake ground motion, okay, and it has U double dot G, we want to know under this ground acceleration, what is the maximum deformation here? How this single degree freedom system is going to displace, how much, right? So that's the point here. So we know, if we know Tn of the system, and we know the acceleration, this is going to be acceleration, and this is Tn, for example, which is the acceleration response spectrum. If we know Tn, then we are going to obtain the value of the maximum acceleration here. We call it SA, spectral acceleration. And then we are going, by making the back calculation of what we have explained before, this SA multiplied by the natural period of the system over 4 pi squared, this would equal to delta. Actually, this is the flip. Do you remember that when we said that A equals to omega squared d, which means that 2 pi over Tn times d. Now this 2 pi over n, to the power 2, raised to the power 2 here. Actually, if you look at this 2 pi over n squared, it's the reciprocal of t squared over 4 pi squared. That's true. So we are seeking for d, which is the delta here. We put it as delta. So this, we can obtain this value, which is delta equal to t squared over 4 pi squared times SA. So let's see it in a clearer form here. So we have this SA is going to be obtained from the acceleration. Okay, this is from the acceleration response spectrum. Okay, so this is going to be obtained from the response spectrum. And this T is going to be given for us. Then we can obtain delta, which is the maximum delta. Okay, the maximum delta. Okay, so now this is T, we said the structure period, and SA, the spectral acceleration obtained from the spectrum, response spectrum plot at period T. We're talking about acceleration. Okay. Then this is the maximum displacement. What about the maximum force? We want the maximum force. Simply, it is nothing to do. The same SA is going to be multiplied by the mass. Mass here is the weight over the gravitational acceleration. So we can obtain this force easy. So if we have a single degree of freedom system, from the acceleration response spectrum, we can get the maximum deformation delta, and we can obtain the maximum force that is going to be applied, which is F, as you used here. Okay, so we have the two terms now can be obtained easily using our main response spectrum, acceleration response spectrum. Okay, now let's go to the calculation of the maximum displacement for multi-degree of freedom system. Now we know that for the single degree of freedom system, but what about multi-degree of freedom system? It is a little bit not tricky, but we need to understand something about multi-degree freedom system, that we have different modes. If we have like different multi-degree freedom system, there is like different mode shapes are going to be occur. Okay, so this is maybe something, sorry for this. So here, this is maybe one mode shape, and this is another mode shape. Okay, so we are not sure which one. This mode shape, it is related to T. We call it T1, for example, the first natural period. This one, for example, maybe it is T2, and so on and so forth. So maybe if we have 3 degrees of freedom, this means that we have 3 natural periods, and we are going to have 3 mode shapes. So in this case, we need to know how to obtain the base shear, for example, okay, and how to obtain the maximum displacement. I'm not going to talk about this issue in detail, because this is maybe it needs some other more explanation, and it takes some more time. But if you recall what I have explained before in dynamic analysis course, we have something called the modal mass. In the modal mass, it is, we are like using masses, but instead of using it just as mass as we know it, but we are going to incorporate the modal amplitudes in it. Okay, so this is the meaning of modal mass. It's not the straightforward direct mass that we use, but it is going to utilize the modal amplitudes. And SA is the spectral acceleration obtained from the response spectrum. It is the same. So if we use modal mass, if we can obtain modal mass, it is dynamic characteristic for the system. It is given to us or known for us. It's not a big deal. You can calculate it easy, and commonly the softwares are calculating it easy. For example, in SAP and STAT and so on, it is calculated easy. Modal mass, if it is normalized, we can use this modal mass to be 1. Commonly this is used in SAP, and then you are going to find that V equals to 1 times SA directly. Okay, Anyway, I do not want you to dig deeper into this part. Just I want you to know that multi-degree freedom system is different in single degree freedom system. Okay, different than the single degree. We need to make some manipulation in order to obtain the maximum base shear and displacement for it. Okay. So in case of multi-degree freedom system, statistical combination rules are used to combine the model results. As long as we have model results, this means that we need to what? To have some statistical combination, representative rule for them in case of the MDF. One such combination, which is very famous method, takes the combined value of the square root of the squares. We call it square root of sum of squares. Okay, square root of sum of squares. So every item from each mode is going to be like raised to the power 2, and then all of them they are going to go under the radical. Okay, this is one of the things of how we are going to do. So if we are going here, for example, to get delta 1, delta 2, delta 3, and so on, this means that we are going to have the square root of delta 1 squared plus delta 2 squared plus delta 3 squared, and etc. Okay, so this is one of the ways for obtaining the representative peak response. When several modes have similar periods, we have different statistical combinations. So whenever that we have similar periods, then the SRSS method does not adequately account for modal interaction. In this case, we use another combination. We call it CQC, complete quadratic combination. Okay, complete quadratic combination. You can find this in the dynamic analysis course also. Okay. Now let's go to the next part. For single degree freedom system structures, response spectrum analysis gives exact. We are talking about exact whenever that it comes to single degree freedom system. But whenever that we talk about multi-degree freedom systems, we are talking about approximate. That's a very important concept. This means that our response spectrum for our buildings, it is approximate, not exact. Because our buildings, they are not single degree freedom system. Okay? They are multiple. So in this case, we are dealing with approximate solution method. The response spectra contained in the building code are called smooth design spectra. We call it smooth. Actually, whenever that you see the response spectra, the real ones, they are making something like this. But whenever you look in the codes like ASCE, for example, we're going to find very nice and smooth response spectra like this. Okay? So actually, this is because the peaks and valleys that are common in the spectrum obtained from any single record are averaged out to form the smooth functional form. This is because smooth response spectrum is using maybe hundreds of actual response spectrum, and they are averaged. So this averaging makes it very smooth. I'm going to talk about this point later. Okay, so don't worry about this. But anyway, the shape of the response spectrum that you're going to see in the codes, it's not jagged one, it is going to be something like this. Okay. Let's go to the last part in our video for today. I'm going to talk about, as I promised before, the pseudo versus true. What is the why we call this is pseudo and this is true, and why there is a difference. Okay. We use them only for velocity and acceleration. So we use the word pseudo for velocity and acceleration, but we do not use this word for deformation. Okay, it's only for velocity and acceleration. Okay, let's go to the basics and let's go to the main differential equation. If you remember this differential equation, we have explained it in the very early beginning of the fundamentals of dynamics in this course. We said that we have here, this is left-hand side is, the first term in the left-hand side is the inertia force, which is m times u double dot, the relative displacement or deformation. And then we have the damping term, which is c times u dot, plus the elastic force term, which is K times U. And here on the right hand side, if we're talking about the ground excitation, we're going to have the minus sign, and here M times U double dot G. This is explained in detail in the previous two videos. Okay, so this is U double dot G, and here this is U relative. Actually they are, if we are going to put them together, we're going to obtain Y total or U total. Okay, anyway, the solution of this equation, this is a differential equation. Our mathematician friends, they solve it for us. Okay, so we are having here our unknown. It is, we want to know what is U and U dot and U double dot, the deformation and the first derivative and the second derivative. Okay, because M is a constant, it's given. U double dot G, it is the input time history record acceleration of the system. It is constant. C and K, they are constants. Okay, so now we want to get, this is our main unknowns now. Okay, generally in the differential equations, we try to find a solution for U of t, which is here. This is using what we call it Duhamel's integral. This equation can be solved using Duhamel's integral. Okay, again, you can revisit the previous videos for understanding the solution. Okay, so here, this is the solution. Do not worry about the integration and do not worry about these terms here, t minus tau and so on. What I want you to be interested in is what are the main parameters that is going to control this U of t. It is omega d. This is d actually. It is, because it's not the natural one, it is the damped one, so it is similar to the w, the omega n. Okay, and then we have the input motion. This is another. Okay, so we can say this is one. This is the second parameter that is very important, and damping ratio. This is 3. So we have the remaining parts are, they are repetitions, so there is no way. So we have omega d or omega, whether it is d or n. Okay, so no problem now. Okay, because there is a little difference between the natural frequency and the damped circular frequency. But anyway, here U of t is going to depend on the natural frequency of the system, the ground motion acceleration, and the damping ratio, right? And from here we can take the first derivative. This is what? Velocity. Okay, this is the velocity, and this is the true velocity. Now we call this the true velocity coming from the equation of motion. When we try to derive this equation, we found that this very long equation here, seemingly that this term is going to be the same as above. And we have here something very interesting. We found it, that we found the first term is going to equal the damping ratio times the natural circular frequency times U of t. Okay, take care of this term. I'm going to indicate it later. And when we are going to take the second derivative, we're going to obtain U double dot total, okay, which is going to be function of minus omega n U of t squared. Take care of this term. Okay, there's a minus sign here, minus 2 the damping ratio omega n U dot. U dot is the velocity. So take care of these two terms that I have highlighted here. We found, okay, by investigation, that this term is going to be dominant for the case of low damping ratios and for the case of the range of single degree of freedom system periods. Okay, so for the periods of interest that we are interested in, commonly we are dealing from like 0.2, for example, to like 3 or 4 seconds. This is the, you know, the range of the buildings that we are commonly encounter in practice. Okay, so we found that, and the damping ratio, commonly the damping ratio, it is going to be also from starting from 0.02, for example, and ending with 0.05. This is another range of the damping. I'm going to show it. So based on these two ranges, we found that omega n ut will almost equal to u dot t, and for the case of this equation, we found that omega n squared ut almost equal to u double dot t of t. So this term is going to vanish and this term is going to vanish, and only we are going to see that these two terms are going to be dominant here. So the point is, let's draw the relation between this term and u dot, which is the true. So this is un times u of t. This is what exactly? This is the pseudo velocity that we have explained before. And w or omega n squared ut, it is what exactly? It is the pseudo acceleration we have explained before. But this one is the true one. Let's draw the relation between the two on a graph and let's see how it works for us. Okay. This is what I said, yes. This is the v here, it equals to omega nd, and this is the acceleration, it equals to omega n squared d. For the velocity, this is what we call it the pseudo velocity, and this one, it is the true velocity. So this term is the true velocity. And here we have the pseudo acceleration, and this is the true acceleration. So we are going to make a graph, the ratio between the two, between this and this, and let's see if they are going to equal one another or not. Okay. Now, this is the first graph that we can see here. This is a graph here on the horizontal axis, it is Tn, and on the vertical axis, it is the pseudo velocity over u dot node, pseudo velocity over true velocity. Okay, go back here, pseudo velocity over true velocity. All of this equation versus this equation. Okay. So we found that this is the curves here. Okay, this is the ratio here, this is the curves. For different damping ratios, we are very near to damping ratio 0. We are almost like 0.02, which is very close to this one. Okay, is in here between damping ratio 0 and damping ratio 0.1 almost. We are in between these two curves. So if you are going to look here, if you are going to look to the practical range of the period, as I said, this is starting from 0.2 almost here, and we are talking about 1, 2, 3. Look here for this range. Almost they are 1. The ratio is 1. They are equal. If you look to all, this is the one that is, it is almost the 1 here, right? Something like this. So almost 1. This means that the comparison between true and pseudo velocity for the range of period that we are interested in, and for the damping ratio that is suitable for our structures, we found that they are the same. So why we bother ourselves with very long equation like this, while that we can obtain V easily from this equation? So this is why we use the word pseudo. Now you can understand why we use the word pseudo. Pseudo, it means that it's not accurate, it's not 100% like this, because we have some differences here, right? We have some differences. It is not accurate, but it is okay for us to use this pseudo because it's very easy. Just omega times d, that's it, it's done. Here, for the acceleration, in similar fashion, we can use the same, that it is omega, it is the true acceleration versus a. We can draw them. We drew them already. Here it is the true acceleration versus, this is the pseudo acceleration versus the true acceleration. We found that for against t, found that they are equal. Where? Look here, we are talking from here. This is the range that we are interested in, and almost 2, 3. We are talking about this one. And for damping ratio, almost 0, between 0 and 0.1. So we are here. So almost we are here, as you can see, it's almost 1. They are the same. They are the same and very accurate. So this is the comparison between true and pseudo acceleration, and we found that they are the same in the particular range that we are interested in. This means that we are okay to use v pseudo velocity instead of the true velocity because they are going to be the same, and it is okay for us to use a, which is the pseudo acceleration, instead of u double dot t, or the true acceleration, because they are going to be the same in the range that we are interested in, as you can see here, or as you can see it here. Okay, so I want to give some hints about this this thing, which is the tripartite, or sorry, for the relation between the pseudo and the true velocity and acceleration. There is a little difference in terms of the magnitude between the pseudo and true values. For the case of low, this is our low level of damping, and within the practical range that of periods that we are talking about. If they are maintained, then no problem for us to use the pseudo velocity or pseudo accelerations. Number two, the simplicity involved in calculating the pseudo values is the main motivation for using them compared to the true values. That's only why we won't use, because as you have seen, true values, they are including like integration and stuff that we do not like. But pseudo, it's only omega times d for velocity and omega squared times d for acceleration. That's it. So it is the simplicity, the main reason. And the widespread adoption of prefix pseudo is in one sense misleading, as you have seen, okay? Because literal meaning of pseudo means false, is not really appropriate since we are dealing with approximations. That's right, we use the word approximate, not false. So the word pseudo is misleading actually. It is not right to use, or at least it's very common to use this word, but I do like to use the word approximated, okay? Rather than with concepts that they are in any sense false or inappropriate. That's right, the word approximate is much more suitable to use in this context. Okay, I think that we are done with our class for today. So I'm going to recap what I have explained shortly. I've gone through the main topics for today, which is I explained in detail the displacement, velocity, and acceleration response spectra, and I explained about the combined displacement, velocity, acceleration response spectrum. We call it the tripartite response spectra, and I give an exposure to the meaning, the difference between the pseudo and true, why we use the pseudo over the true, and what is the misunderstanding regarding the word pseudo itself. I hope that you like the video, and see you in the next video.